Well, I think we're about there. Welcome back, everyone. For today's class, we can kind of see what we're getting into. We're just about done with section 4.1. One last problem on the closed interval method. The last problem is a pretty tough one, I would say. So this will help out quite a bit with the last problem as well on WebAssign for that section. Then we're getting into optimization. Section 4.2 is a pretty big section. It's slightly more technical, but in a nice sense, it's kind of a big review section as well. We're going to pull information from section 3.2. That's why you see the tab open there to see what's going on with the optimization. The section title just says how derivatives affect the shape of the graph, but it's important to think in terms of this is what it's all about. We're actually doing real honest optimization problems, except there's no context on these. This allows us to focus on the actual math and methods. Then in the very next section, there will be context. We'll be looking at things from the sciences, biological sciences, pharmacology, engineering, business, that kind of stuff. So that's going to be our goal for sections 4.2 and the next one right after. Then probably the bigger announcement is we haven't had a quiz in a while, just various little things like exams coming up, spring break coming up caused us to push for a bit on these quizzes. But here's the very next quiz. Quiz number 6 is going to be due next Thursday. It'll be the 1 week turnaround pattern as before, but I feel like that it deserves emphasis because it has been a while. But any last questions at all, folks, before we get going with today's work? Okay, well, we're on the last problem with section 4.1. Even though I'm calling 4.2 optimization methods, the closed interval method in the prior section is an optimization technique. It finds the absolute maximum and the absolute minimum. So here's where we left off. I carried down the closed interval method down to this spot. Fun fact, or maybe not fun, but important fact, this is basically what quiz 6 is all about, doing this again for another fresh problem. This time, we have a function x times e to the power negative x squared over 8 on a closed interval provided. That's good. We want a continuous function on a closed interval, and that's what we've been provided. We want to know the absolute maximum and absolute minimum values of this particular function. So to get started, step 1 says we need the critical number. And the penned-in comment right here says if step 1 is a critical number, then really what you're doing to get started is just cranking out the ordinary derivative. So basically the methods of chapter 3 on our very first step. Compute f prime of x. Now notice this is not a nice derivative by any means. It's not terrible, but we still want to be careful with this thing. Very first relevant rule is product rule. So let's start by organizing and saying this derivative is going to be the derivative of x, just a 1 there, times e to the negative x squared over 8 plus x times, this is the not as nice step, e to the negative x squared over 8 prime. So this will be our method right here. And let me just add some parallelism to my color coding. Okay, so first derivative over here, not so bad. That one's just a 1. So on our next line, we would write in derivative of f at x equals e negative x squared over 8. Since this derivative is 1, and 1 times this just gives back that base e exponential, then plus x times, at this stage, I would want to do it slightly more carefully. So let's organize this one. This is a chain rule problem, and if you can just see it and know exactly how it comes out, good on you. That's the goal to get to that step. This is a tricky one, however, because of the exponential format. This is the inner function right here. Base e exponential is the outer function. So let me know how you feel about this derivative right here. These ones through the chain rule, in my opinion, are always pretty tricky. If I differentiate this, I would go e to a power. That's doing the outer derivative. Then the chain rule says multiply by the derivative of what went inside here as an exponent. So we go now to the inner function, copy in that negative x squared divided by 8 into both spots. But the way you copy it in actually really does matter here. Where the red dot is right now, I copied it in a way that's just easy to write in. It's easy to see. But if I copy it in the same exact format right here, it makes the derivative tricky. So let's change the formatting to write negative x squared divided by 8. That's nothing but negative 1/8 times x squared. And this clearly displays we're just going to be using the constant multiple rule and the power rule when we crank out this last derivative. So putting this now all together, we have derivative of f at x is e negative x squared over 8 plus x times e to the negative x squared over 8 times this derivative right here. It's not too bad. Constant multiple rule would say we get negative 1/8 to start times over here, power rule will give us 2 times x power 1, so just 2x. And that's starting to look like a nice cleaned up derivative. We're just going to simplify it a little bit more. And also keep in mind, we're only on this step right here. We're finding the derivative. Next step is to set it equal to 0 and solve, but we're getting there. Step 1 is where most of the work happens in the closed interval method. So now finalizing this, we have f prime of x equals, looking at this format, if you see a greatest common factor, and you know you're going to eventually solve an equation set equal to 0, you definitely want to factor that out. So let's begin by factoring out e power negative x squared over 8, leaving behind, from this term, there'll be just a 1. Visualize redistributing this back in to get the result down here. And now, when I factor out e negative x squared over 8 from this position, I'm left with x times x, so there's an x squared, and this constant is negative 1/4. So it's going to be plus, let me fix that, didn't look before I left, minus 1/4 x squared. Again, power 2 on x comes from this x and this x. E negative x squared over 8 was factored out, so it's just gone. And I simplified this fraction as well to get the negative 1/4. Does that look right to folks so far? Okay, basically just a redo of another random derivative from chapter 3, where the only thing I did additional from chapter 3 was I also factored out e to the negative x squared over 8, which is a smart move because we're now doing this part. Set your derivative equal to 0 and solve. Okay, we've got it set to 0. We're ready to solve this thing. The reason factorization is so important is we're using the zero product property. If two things are multiplying together, here's the first thing, here's the second thing in the bracket, to result in 0, then that means two possibilities occur. This implies immediately e negative x squared over 8 is 0, or 1 minus a fourth x squared is 0. In other words, a factorization implies only if you have a 0 right here, you can split up into now two equations. Essentially, it's a divide and conquer kind of algebraic technique, because this equation and this equation are easier to solve on their own. This one's super easy to solve. Let's take a look into some graphics on that one. Anytime you're dealing with any exponential, not just a base E one, any exponential whatsoever, you have an awesome property. Let's write this in as y equals e power x. The property of this exponential is that it never actually hits 0. That's hard to see, right? If you're way out here, eventually Desmos is going to approximate 0, but it's an approximation. It's just a finite device. No number you put inside here directly results in 0 whatsoever. And you could really try, go e power negative 100, for example. Even at power negative 100, this is what you get, 3.72. Notice the order of magnitude on the scientific notation, really small number, but it's still positive. So back over here on this equation, what I would say if I saw this, I would just write in no solution. And this is because e to the a greater than 0 for all, not for that. Let me say for all a and r. I think making a better sentence makes that a little bit more clear. So e power of a always positive means we couldn't get a solution here. We just move on to the next equation. That one's definitely solvable. And a lot of ways to solve this. We solved something like this on a prior example, where we just isolated x squared, and that would work on this one as well. But here's a whole new approach. Clear the denominator by multiplying everything by 4. We'll get 4 minus x squared equals 0, because multiplying the right-hand side by 4 is no change. Then over here, instead of isolating x squared, let's go the factoring method. You could write this as 2 plus x, 2 minus x. You don't have to go this method. It's just an alternate way to solve this one. And now once we're down here, same issue that happened up here, just a nicer version to look at. Two things multiplying resulting in a 0 will always give you one or the other is 0. So 2 plus x is 0, or 2 minus x is 0. Finally, we get to say x equals -2. The comma here takes the place as a or it's +2. Whew, that's a lot of work just to get critical numbers on this thing. But now that we have them, step 1 is done. Step 2, step 3, really rapid to complete the rest of this. However, are we really done with step 1? The whole purpose of step 1 is find the critical numbers. So let's say here, the critical numbers of f are, let me fix my English here, is x equals, there's actually just one of them. Anyone spot the correct critical number from that list? But one of them actually doesn't fit. It's kind of surprising in a way. Turns out 2 works. 2 is the critical number of f. So what's wrong with the -2? That's kind of a weird question in a certain sense, right? But the thing that we have to remember that's easy to miss on this kind of problem, so watch out for this on a quiz, is that the closed interval method deals with a continuous function on a very, very specific domain, the closed interval AB. Our closed interval is -1, 4. That means -2 is out of domain. We just have to throw it away. So let's make a big comment on that one. -2 is out of domain. And when we say out of domain, we're referring to this closed interval here. This is the domain. This doesn't happen on every problem, but when it does happen, it's kind of a strange thing in your algebra. So watch out for those weird little situations occurring. So we've done it, folks. Step 1 is completely done. Step 2, all we're doing is function evaluations. We find the values of f on the endpoints of the interval, that's -1 and +4. Any critical numbers we found, that's 2. And then largest value is your absolute maximum, smallest value is your absolute minimum. So those are the last steps we'll take. Any questions at all, folks, to this step?
Confused where you drew that black arrow to the next.
Oh, gotcha. Yeah.
What did you do there mathematically?
The major first thing I did was I factored out the e-(x²/8. So if I kind of did the pre-factorization here, it would have worked or looked like this. F prime of x equals e-(x²/8 bracket. We're essentially dividing it out. So there's a 1 here now, plus x. It's gone from here, and it leaves behind the -1/4 times x over here. So factoring that out gave us this bracket. And then all I did was multiply x to x to get that x² there.
There's, so you took the derivative of -1/8 times x².
Yeah.
And then that just stays with -1/8 times 2x.
It does, yeah. It just looks funny because of the fraction. But if you take another look at this one and work by analogy of what if it was a function y equals -8x². In that case, y prime would have been -16x. Or maybe writing this out in a better way, it would have been -8 times 2x. So whatever the number is right here, constant multiple rule says in affected by the derivative, it still is going to multiply. Take the derivative of x squared, 2 will come down, you get power x. And that's what we got right here. Negative 1/8 is just a weird constant to look at, but the derivative of x squared gave us that 2x right here. And this is just simplifying the negative 1/8 times 2. Does that help to see that derivative there? Gotcha. Other questions at the moment? Okay. Yeah, lots that happened on that black line. Thanks for mentioning that and kind of slowing down the analysis on this one. We did two big things. We factor out e negative x squared. We had the derivative computed, but we also simplified it at the same exact time as factoring it out. So lots of stuff happened there. And I agree, this thing is a nasty chain rule. One of the reasons we're talking about we write in negative x squared over 8 this way is because we want it to be compact for the exponent. But then we totally change the format because it's not an easy derivative to even look at in this form. It's not a quotient rule, just an ordinary constant multiple rule, much like if you're doing this derivative as well. So last thing we need to do is take this critical number, domain values. Let's call this step 1. And now we are on step 2. In step 2, we calculate f at one boundary value, -1. Let's do this right here. And notice this is actually kind of tricky in a way. When we refer to f, we're talking about the original function f of x, but it's tempting to look into that one because we worked so hard on calculating it. It's not relevant here anymore. All we wanted was the critical number. So now we're just back to this function at the end of the analysis. Plug in -1 and we'll get negative e power -1 squared 8. So this will be negative e to the power of -1/8 on the first one. Calculate f at the critical number. Let me hide that like that one yellow to say it came from the domain. Here's the one in blue, the critical number. Plugging 2 back in here, we have 2 e to the power -2 squared 8, which is 2 e to the power of, let's see, that's going to be a 4 divided by 8, so -1/2. Then last, let me see if I can scroll just a touch here. We go to the upper boundary value, compute f at 4. This is going to be equal to, back to the function f, 4 e to the power of -4 squared 8, which is equal to 4 e to the power of, let's look at this again. 4 squared is 16 divided by 8 would be 2. So that's just power -2 altogether. So we have all of our exact values down line. All I could tell you for sure is that this one's negative. The other two are positive, but I couldn't tell you which one is larger. I think this one is a good guess for it being larger, but it doesn't take into account that the exponent is different too. It's actually kind of hard to tell. So this is the standard reminder. Don't forget that a calculator is allowed on exam 3. We would absolutely need one for this. Let's put in some function values. Negative e power -1/8. That one's at -0.88. Now 2 e power -1/2. This one is at a 1.21. And last one, 4 e power just -2. This one comes out as a 0.541. That's kind of surprising as a way. What it's telling us is that e -2 is so small as a number compared to e power -1/2. But even though the coefficient in front over here is double the one above, the number is still smaller. That's because as you put large negative numbers here, it goes to 0 quickly. But keep in mind, it never actually hits 0 like we were mentioning in that comment. That's the conclusion on step 2. And step 3 just says, pick your largest value for your absolute max, pick your smallest value for your absolute minimum. But any questions at all, folks, on step 2? Okay, so step 3, all we're doing is finalizing this, just stating a conclusion, basically. Step 3, we might say something along these lines. The absolute maximum is equal to this one right here, the one that corresponded to the largest value, 2e power negative 1/2. Then next, we can say the absolute minimum is going to be this one. If there's a negative in the list, that really indicates it. But notice I'm picking the exact values, negative e power negative 1/8. Don't forget when you go to report these values, this is the most annoying thing about the whole process. We must give the exact values. So even though these are decent approximations to the nearest hundred, this is what we're really going for. The actual exact absolute maximum, exact absolute minimum. So that's a whole process. It is a pretty long process if the derivative is really involved. So this one was a pretty big one. But you might have noticed in the last example that we did, we were able to solve that one in about 6 or 7 minutes. Any last questions or comments, folks, or on the conclusion for this one? Okay, next thing you probably would want to do for any problem like this is, once you get down to the end here, this is really good practice. You'll have to do this as a quiz problem, but more critically, you have to do it this way as an exam problem as well, going for those exact values. On the exam setting, we don't have access to this technology, graphing calculators or Desmos certainly. But when you're learning this, say quiz problems, WebAssign problems, really good idea to just go through the whole method that we did and then just double check how accurate we got. So let's take in f of x, xe power negative x squared over 8. Let me see if I did that right. Negative x squared, there we go. Divide by 8, that's how it should have been. This has a specific domain, so we'll say negative 1 less or equals to x, less or equals to 4. And it looks like we've got that whole function inside. Let me see here. So from negative 1 to 4, yeah, I think we've got it. Now let's take a look at what we said on our listing right here. We said the absolute maximum of this function, 2e power negative 1/2. And we also approximated 2e power negative 1/2 to a 1.21. That tracks with what we see on the graph. Minimum is this value. And there we go. It's about a negative 0.88. That's right at the end of the domain. So that's one that WebAssign or Desmos doesn't even want to let me hold as a point there. So we do get the negative 0.88 as we got here. So we call that the absolute minimum. It's kind of neat to see the technology telling us that what we got to after doing all of that work really was accurate, satisfying in a way. So give that a try when you're learning it. It'll help quite a bit. But keep in mind on quizzes and exams, we have to show that whole process here. I think that's all we have to say about that section. Any last questions or comments at all, folks, on the closed interval method? Okay, well, that's one section down. Now we're going to the optimization techniques, section 4.2. So let me close this out. Part of this is essentially a review section, which is definitely welcome for all these ideas. Here, we're going to be reviewing some concepts that we looked into even in chapter 2, as well as chapter 3. So first, here's the definition of the derivative out of nowhere, which makes sense. The section title is how the derivative affects the shape of a graph. So we should have the derivative defined. That's a big definition right there. The whole purpose of chapter 3 was to show efficient ways to calculate the derivative. But it's also good to know what is its formal definition. And in particular, this is what it represents geometrically. If this derivative f prime of x exists, it will give you the slope of the tangent line right at x for every single value of x. Then, with this idea, we can say if the derivative is bigger than 0, the slope of the tangent line is bigger than 0, so your function's increasing, and vice versa for a negative derivative. Negative derivatives means tangent line is sloping downwards, but that only happens if your function itself is going down, decreasing. So that's the whole idea with the increasing decreasing test. And in fact, we've used it more than once. We used it right here in section 3.2. Let's just throw this in as a quick screenshot to help identify these ideas. I'm taking the original function f of x because this is less about graphing the derivative down below. I feel like that'd be a distraction. So here's our way to look into increasing decreasing test. The result of this test is just following the logic of what's highlighted in yellow. And we can see this right here. If I'm on this point at any point, tangent line goes this way, it's a negative slope. So we say the derivative is negative, and that corresponds with the function itself decreasing. Here we have the local minimum, so there is no change in increasing versus decreasing. It's like a point where it transitions to now increasing. Here the tangent lines go like this, they're positive, meaning the derivative is positive. But at the same time, we can clearly see functions increasing as well. Then it turns around and does the opposite and so on. But that's the idea of the increasing decreasing test. That's what allowed us to plot this in the very first place in a certain sense. Any questions, folks, about that reminder on that test there? Okay, what makes this test really actually new is that we've never done it in a problem like the one down below. So we have never applied the increasing decreasing test to something like example 1. Example 1 says, well, we have a function f, degree 3 polynomial. They get complicated on their own. And we're looking for the intervals where this function is increasing and where it's decreasing, which means we'll directly use the increasing decreasing test on this part right here. But then the purpose of the increasing decreasing test is directly related to the first derivative test. So here's our first optimization method. This one is fine-tuned to local maxes, local minimums. And in the very next chapter, we're going to adjust it for absolute maximums, absolute minimums, like in the closed interval method. So think of this as a practice run, and then we'll adjust it again in the next section. First thing we look for is a critical number. That's basically a hint on the exam. If you're stuck, you don't know where to start, just get a critical number. You're probably getting a lot of partial credit on that problem right away. It happens so often as a statement. Once we have the critical number, we're looking for sign changes. If f prime changes from positive to negative at c, well, that means it changed from increasing to decreasing at c. We would have a local maximum. If f prime changes from negative to positive, that means it went from negative to positive. That means it went from decreasing, that's the negative part, to positive. The derivative is positive, then it goes to increasing, and that means you have a local minimum instead. So that's kind of the logic of first derivative test, increasing, decreasing test. What we'll do next is first find the intervals where it's increasing, decreasing, find the local maximum minimum values of f. That's just using this test right above. Any questions at all, folks, before we give this one a try? Okay, so this is our first really big optimization problem. Third degree polynomial, there's no context here, but what you want to imagine is we're later going to do a problem like this one, slightly different function, but there is context behind it. So this is like a warm-up to those methods. We'll come back to the first derivative test for the moment, but at the moment, it's all about increasing, decreasing. First thing we do is we find all the critical numbers of f. So begin with f prime of x. A little bit faster on this one, right? So this is kind of a break after the last problem we computed. We'll get 6x squared minus 18x plus 12. then essentially we're doing this step of the first derivative test. We want a critical number. So we calculated the first derivative. Now we set it equal to 0. Before we set it equal to 0, I want to backtrack just a little bit and say, let's also simplify it as much as feasibly possible because we have to work with that a lot. One thing I can see already is we can factor out a 6, and that's pretty beneficial. That'll leave behind x squared minus 3x plus 2. Next, this polynomial factors in a nice way. And in an exam setting, that is the expectation. I'm going to give you stuff where you don't have to use a quadratic formula to find a factorization. It should be a clean factorization like this. It's going to be x and x for the x squared part. 2 is fantastic here. It's prime. So my only good option is 2 and 1. Positive here with negative here means signs are negative. And if we double check this, multiplying here to here is negative x. Here to here is negative 2x. They sum total to negative 3x. And so that tells us that's a bona fide factorization. So there's our first derivative in its most simplified form for our current task. We want it fully factored because our next task is set it equal to 0 and solve. Let's do it right here. So now it's set equal to 0. This will imply either 6 is 0, that's impossible, skip to the next factor, or x minus 2 is 0, or x minus 1 is 0. And if you didn't like that 6 there, you can just divide both sides by 6. Now it's gone because 0 divided by 6, still 0. Then from over here, we can say this implies x equals 1, 2 are the critical numbers of f. So we've got that step down. Even if we're just doing the increasing decreasing test for where it's intervals where it's increasing, where it's decreasing, we still need those critical numbers. So now we're going to apply this test right here. Very first thing we're going to do is draw a number line. This is a function with domain all real numbers. It didn't give us a closed interval. So we're going to assume that it's defined on something that goes like this. From positive infinity to negative infinity. So here's our number line. These critical numbers are essentially now just cut points. They're places where we're going to directly cut up the real number line. One cut at 1, another cut at 2. The thing that we're estimating in now 3 different regions is not estimating. The thing we're looking for the sign of all those 3 different regions is the derivative right here. So we want to know what is the sign of the derivative here, here, and here. Next thing we do is we just use test points at the next step. In order to resolve what the sign is of the derivative on this infinitely long region, we only need to pick one convenient point. That's kind of amazing in a way, but the reason that's true is there is only 2 points where the derivative goes to 0. So if I find it's negative here, it's negative for all of time. The only way it could flip to positive is if it crossed the x-axis, but that's possible. The only crossings are at 1 and 2. So let's test out at 0. Notice you want to make your actual critical numbers kind of bold, make them stand out. Make your test points kind of small and diminutive so you don't actually grab them when you give your conclusions. They're just a test point. They're not part of the conclusion altogether. So go f prime at 0. F prime starts here, but in its most convenient form, it'd be this function because you can just throw 0 in there right away and get an output 12. It's greater than 0, so that tells us f prime is greater than 0 here. And so we are increasing in that range from negative infinity to 1. When we hit 1, the derivative is 0, so there's a horizontal tangent line. If this goes to less than, we have found a local maximum, but it could maintain the direction to still positive. Just depends on the function. So we have to test again. maybe 1.5 would be a good thing to test out. Do f prime 1.5. And I wouldn't want to put 1.5 on this line. That's annoying. Put 1.5 way out here. This is the convenient side of the function for the next task. That's weird, right? Depending on what you're inputting to the function, it tells you which format of the function we should be using for the derivative. 1.5 is convenient here because I can just go 6. 1.5 minus 2 is a negative 0.5. 1.5 minus 1 is a positive 0.5. And we don't even need to know what the number is. We just want the sign of the number. It's negative because there's only one negative there. So I'll go less than 0. Up here, go less than 0. Take a look at our guide right here. If the derivative is less than 0, f is decreasing. So just a really quick notation. I'll remind myself decreasing here. Then that was so fun. We just rinse and repeat. Any questions first, folks, with that conclusion there? Okay, one last one to test. But now that we are essentially testing all the intervals, let me give you a shortcut. If you're one that has done this a lot and you do know the shortcut, you just want a refresher. Look over here. All the powers are odd on this. Power 1 is odd, power 1 is odd. Doesn't matter on this one because x didn't occur. If the powers are odd, then the signs will always alternate. One even power throws off the pattern. It'll maintain the sign across the interval. That's why its best strategy is really to just check them out and be careful. But this is an expectation already. I'm expecting positive here, greater than 0, which would mean if f prime is greater than 0, we're increasing. If I wanted to be extra sure, I would probably grab a point like maybe 3, compute f prime at 3 just to be sure. Again, this is the most convenient one to throw a 3 in. We'll get 6 times 1 times 2. That's a positive value. So we did get positive as expected. Well, any questions at all, folks, with our interval completely filled out? Okay, maybe one word of warning on this. It's one thing to see it done once on paper like this, but showing work is required on quizzes and exams. So what does this have to do with anything? It means the way you do this on WebAssign absolutely matters. On WebAssign, show these steps as well for practice. Since the WebAssign problems are useless essentially, unless they're helping us practice for the exam, and these are the steps that we would have to show. So when it says show these steps, what I'm referring to is this right here. We have to have some kind of way to indicate the sign of the derivative changing. It might be in this kind of format. You might have a different way that you prefer to do it, and that would be totally fine. But any way that shows a systematic process of determining these 3 signs is expected on the exam as well. So if we don't do it on WebAssign, it means the exam is now extra, extra hard. There'll be also an expectation on quizzes. So that's the, well, not quite done. That's the whole use of the increasing decreasing test. We just need to state our answers. Intervals where f is increasing, intervals where f is decreasing will give us this answer. Let's say here, f is increasing on the interval from negative infinity all the way up to 1, but not including it. So go negative infinity, comma 1, and there has to be parentheses around both of them. Around 1 because right at 1, f is not increasing nor decreasing. It's in transition. It's at rest, essentially, right at that time. We start increasing again right at 2, so go union, 2 comma infinity. Then last thing to say, f is decreasing On just one interval, it goes from 1 to 2. So we did it, folks. That's the entire use of the increasing decreasing test. Big takeaway is positive derivative means an increasing function. And so that's how these conclusions went together. Any last questions at all, folks, on running through that whole analysis in part A? Okay, well, the point of this whole problem right here was not the increasing test really. The major point was it's about optimization. Once we have something like this determined, or intervals like these determined, we can now say with definitive proof and evidence what the local minimum and local maximum value is of f. We can determine those values exactly now. So even if we double check on the graph is just giving you approximate values. We will know the exact value of the max and the min. Now, we don't use this function any longer. That was just to come up with the increasing, decreasing intervals. We go back to the original function f of x. So let's take this whole thing as a screenshot maybe. And finish out the last bit. Once I find a spot to zoom to, let's see here. I want that down there. And you know what? The intervals was the punchline to part A. I think this is an easier chart to look at actually, if you're about to use the first derivative test. So let's use both pieces of information here. Give me one moment. Okay, I think we've got a good scroll here. With the sign chart, the original function down below, we're ready to answer part B, local maximums, local minimums. First, this is something that you could do if it's helpful. So on your sign chart, when we said the function was increasing and then went to decreasing, that meant if you were trying to graph that function, it looks about like this. That's a little bit extreme. Let me fix the pen. The function looks about like this. There is a local maximum right around here as it went from increasing to decreasing. So this bold line in orange is me imagining what the plot of the graph would look like. Definitely not an accurate plot, but it captures the increasing to decreasing across one. The first derivative test just says we change from positive to negative, which therefore means you are increasing and then decreasing, you have a local maximum. Or you could just stare at your sign chart. You can kind of see it. There's got to be a maximum there based on what the function is doing. So we'll say f, or let's do it this way. We have a local max, which is equal to f at. Now we take the critical number and throw it in, f at 1. But when we say f, we're not talking about the derivative. We're talking about the original function down below. We're trying to optimize that one. So this will be, insert a 1 inside there. 2 times 1 minus 9 times 1 plus 12 times 1 minus 3. That's going to be a 2 exactly. So we have a local maximum at exactly 2. Then we just redo this all over again. For the next part, right around 2, what did the function do? It was decreasing. So here it is decreasing. At 2, it's at rest, and it changes to increasing. So we have this kind of graph right around 2. The first derivative test says if f prime changes from negative to positive, which is what we did, we have a local minimum. Or you could just say if you're decreasing and then you switch to increasing, there had to have been a minimum around there. So that's the logic of the whole test. And that's why we have a minimum, a local minimum next. We'll say the local min is f at the other critical number, 2. We're plugging 2 into that thing. So that's 2 by 2 cubed minus 9 by 2 squared plus 12 by 2 minus 3. It's a Thursday, so let's treat ourselves to a calculator on that one. So this is 2 times 8 minus 9 times 4 plus 24 minus 3. Looks like we have a value of 1 exactly for the local min. So that's the full analysis on this one. Didn't mean to scribble on that. And that ends the problem finally. We have a local max, local minimum, and we haven't even peeked at the graph even once. We'll totally do that just to see if we're on the right track. But any last questions at all, folks, running through this analysis? Okay, just to make sure there's not a bunch of hanging little screenshots at the end of the notes. Let's now take a look into the original function and see if these conclusions even match up. Let's see how well they hold. So back to the original function, which is this one. We'll define f of x to be 2x cubed minus 9x squared plus 12x's minus 3. This function has domain all real numbers, so I wouldn't add anything after that. Let's take a look into a local maximum. Local maximum would occur right here. 1 is not the local maximum, it's the second coordinate 2, so 2 is the answer here. I wrote in f of 1 because that's telling us what you calculate to actually get that local max. Then it's decreasing forever to the left. That's why we didn't get anything to the left of 1, the input 1 there. But at 2, we got a local minimum. And there it is at height 1, matching up with our answer down there. The output of 1 is the local min. In a way, it's kind of satisfying to see, again, the work actually panning out on this. So give technology a try when you're working on these. It really helps out sometimes as just a double check. Well, for the next concept, we're going to be dealing with something called concavity. I feel like concavity is something that is kind of vague just in its definition. Sometimes other textbooks redefine this differently. So if you've heard words along the lines of convex versus concave, we're talking about the same kind of concepts. Our author goes with concave up versus concave down. And we have some nice definitions down here. Let's read through them. It says, if the graph of f lies above all of its tangent lines on an interval, f is concave up. And if the graph of f lies below all its tangent lines on an interval, f is concave down. But if you're like me, you might not have gotten too much out of that. That's kind of hard to visualize just by reading the definition. Some people can do this, and if that's you, I think it's awesome. But for me, if I was really trying to learn this definition, I need an example immediately. I can't just imagine a random function and random tangent lines around it. So let's get our function right here. This will be a double use duty, this curve. Let's think about concavity on about this region right here. So I don't want the full domain, just a restricted domain. So if we can understand concavity through this graph, that'd be a great way to understand these two elements of the definition, concave up versus concave down. The last thing we didn't talk about is the inflection point. The inflection point on the graph is a point, let me say from the start, a point is an inflection point. If f is continuous there and the curve changes from concave up to concave down, or if the curve changes from concave down to concave up. In other words, an inflection point is a point on the graph of f where concavity changes. Let's say it this way. A point where concavity changes. Okay, now let's give this a try. Let's take a look into concave up. It says concave up means graph of f is now above its tangent lines. So let me start writing in some tangent lines. Easiest ones to put in are the horizontal tangent lines. There'd be one right here. Another horizontal tangent line right here. And this gets us started. On this part of the curve, does it look concave up or concave down? Anyone see the difference? Good call from the class. This looks like concave down. And that's because this part where it says Graph of f lies below all its tangents. That's what's happening right here. I only drew one tangent, but the graph is clearly below that tangent. We have to watch out for the inflection point though, right? Because in this region, concave up, it's above the tangents. Well, the one tangent that we drew in. So somewhere in the middle here is a transition point where it had changed from concave up to concave down. Really hard to see it visually just by eyeballing all of this, but we're going to try attempt to the possible and visualize that transition point. Maybe the next thing to do is, let's just add a few more tangents. If you were, say, way out here, tangent line would look about like this. Still going to be, below the tangent line. Looks like no matter where we're at on this one. For over here, tangent line would go about like that. Over here has a tangent line going about like that. But you know, once I start plotting right around here, maybe, I'm not too sure where the tangent line is going to be. Above and below, maybe in parts, one side's above, the other side's below. But it's only in regions like out here where it looks like my curve is now above the tangent line. Out here, it was below. The inflection point is somewhere around here. I'm just visually guessing maybe about at that mark. Other tangents might look like this. So we can finally put all this together and say, let's see here. It's concave up if it's above its tangents. And that seems to happen on about this range. From here to here, concave up. Because once again, right around that range, we are above our tangents. That highlighter might be a bit of a distraction, but just a temporary visualization. Then next, from here on out to somewhere right about there. Again, this point isn't perfectly placed. We need calculus and algebra to find its exact position. But from here to here, we have concave down. And again, concave down just because the curve appears to be always below its tangents. Any tangent we pick, up until right about there, the curve is below. So that's the idea of concavity. What this tells us is a nice way to define it. It is through calculus because we put tangent lines down. But if we had to take this approach and compute a tangent line on every part of that curve, it's an enormous amount of work. So there's got to be a better way, and there is. This is kind of weird. Concavity is encapsulated in the second derivative. So that's going to take us to the second derivative test next. But any last questions at all, folks, with the core definition here? Okay, so this definition tells us what we're looking for when we're thinking about concavity. What does it actually look like? And then this definition tells you how to actually compute the intervals of concave up, intervals where it's concave down, which will then inform you what the inflection points have to be. The inflection point is a point on the graph where concavity has changed. Kind of a nice, satisfying definition, right? If the second derivative is positive, concave up. And if the second derivative is negative, we are concave down. So that's actually a fast kind of computation. Word of warning though, the second derivative also has an optimization technique. And in this optimization technique, the second derivative test, conclusions go backwards. It's as hard on the brain. Positive derivative here leads to a local minimum, and a negative derivative here leads to a local maximum. We have a lot to explain just on that. But I feel like this is good to get out of the way immediately, because conclusions on second derivative test go backwards from your possible expectations. However, if all you're doing is concavity, your expectations match. Positive to concave up, negative to concave down. So let's give this one a try. On example 2, we'll find intervals where it's concave up, concave down. Part B, we'll find the inflection points. But when you do this problem, it's really similar to the example 1 of the day, where we're just finding local maxes, local minimums, and then just end the problem. Here, part A is kind of like finding intervals of increase, decrease. Part B is kind of like finding the locals maximums, local minimums. Really, the only difference in the methods are we go to the second derivative. So that's the major change here. So if we're using the concavity test, step one, find the critical numbers of not f. We want the critical numbers of one derivative order higher, f prime. Let's just explain what that means. This means solve f double prime x set equal to 0. So that's how we find the critical numbers of the higher thing here, the derivative itself. If we set f prime of x equals 0, we'll find critical numbers to just f. And that pattern just keeps on going. If we're setting the third derivative to 0, we'll find critical numbers of f double prime and so on. But this informs us what to do. We take the original function, calculate the second derivative, which means we have to start off with the first derivative, f prime of x. And this is a chain rule problem as well, so let's be careful with it. X power 4 plus 27 is the inner part. Natural log x is the outer part. And just a reminder, it's been a while, the derivative with respect to x of the natural logarithm of x is just 1 over x. So that gets us started. Take the derivative of the natural logarithm, it's 1 over whatever the input is, multiply by the derivative of that input, take the inner function, x power 4 plus 27, it'll go in both of the placeholders, excuse me, and f prime is essentially done at this step. Denominator is going to stay exactly the way it is. And we'll push this into the numerator since it's multiplying. It's just going to leave a 4x cubed. So when part of step one is done, we have f prime, but we need to solve f double prime set equal to 0. So that's the next thing we calculate. Any questions first on the first derivative? Okay, so now second derivative. Pretty good review on differentiation techniques, just doing that second derivative. It is a quotient rule. I'm going to avoid the color coding because this is the new concept color coded already. Let me just show the structure. For doing quotient rule on this, we'll take the derivative of the top, multiply by the bottom copied in, minus the top copied in, multiplied by the bottom differentiated. So just like product rule, but a minus in the middle, and then divide by that denominator squared. So x power 4 plus 27 squared. So this is our first step. Next step, we're computing those two derivatives indicated with the prime symbols. This one is going to be 12x squared, multiplying x power 4 plus 27 minus 4x cubed times, this is another 4x cubed. And denominator, no change. Yeah, I miscopied it for a moment there. X power 4 plus 27 squared. Now, if we were in chapter 3, I would have given full credit to that. In fact, I did that on a couple exams on exam 2. But in chapter 4, that's not good enough for us. If we try to use that function in the concavity test, it's going to be really, really painful. I won't even be able to do this in a reasonable way. We want critical numbers to this. So our task next is simplify this as much as feasibly possible. So here's our next line. F double prime of x is going to be equal to, first let's distribute. That's going to be 12x power 6 plus large number, 27 twelfths. 27 by 12 is a better way to say that. So 324 on that one there. X squared. Then over here, this is going to be minus 16. X power 6 all of which is divided by x power 4 plus 27 squared. All I've done here is distribute this group right here, multiply that group. Next thing we can do is combine our like terms. I want to make positive being my leading term, so I'm going to start with 324x squared. 12x power 6 minus 16 of them is going to be minus 4x power 6. X power 4 plus 27 squared. Now we do the factorization step. X squared can be pulled out. We want the greatest common factor, so let's test division. So if I can divide this by 4, it means 4 factors out. Let me show this in maybe a better way. 324 divided by 4 gives us 81. So we can factor 4 out of that very first term there. Let's take out 4x squared. It'll leave behind 81 minus x power 4 from this term. And below x power 4 plus 27 squared. Just keeps on going, but we're getting there. Let's scroll a bit more. So this is in a nice simplified form, but if we're equation solving, it's still not there. This factors. So next step, f double prime of x equals 4x squared. This factors as a difference of squares. We can go 9 plus x squared, 9 minus x squared. If we FOIL that result, we just get back to this one up here. Then it's again divided by x power 4 plus 27 squared. And we factored it even more. This one is a sum of squares. It doesn't factor over the real number system, and we're avoiding complex numbers, so that part's done. But this part's still a difference of squares, so we take it even further and go 4x squared, 9 plus x squared, factor that part by the red dot over here as 3 plus x, 3 minus x. All over x power 4 plus 27 squared. And we're now in business. We set this equal to 0 because it's in its most simplified form. And we can solve this very rapidly. We made a comment about this, in fact, in the prior section. If you set a fraction equal to 0, then the only possible way this equation is true is if the numerator is 0. In other words, the denominator has no influence whatsoever on the solution of a fraction set equal to 0. So let's look into the numerator. Our last line implies the only way you're getting 0 on this is if you put 0 right there. That would wipe out everything. It'd be 0 divided by 27 squared. Whole thing is 0. So that's one critical number. It's impossible to plug in a value for x that makes this one 0, as long as you're using real numbers, which we're constrained to. So we move just to the next group. -3 would do the job there. It would force it 0. And on this one, a +3 would do the job. So that's the full set. 0, -3, +3 are the critical numbers of f prime. You could just say they're the critical numbers, but saying they're for f prime reminds us that we're solving for concavity, not where the function is increasing or decreasing. This is the major work towards that. Now we scroll up, grab the concavity test, and finish out the rest of the problem. At this point, you might have a bit of deja vu. Like we were mentioning, the concavity test is very similar in the methods that we use to the increasing-decreasing test. The only difference is we go to the second derivative. So once you get critical numbers, here's the next thing we do. We draw in an interval that goes like this, from -infinity off to +infinity. The critical numbers just found are now cut points on the real number line. We'll make 3 cuts, so now we have 4 intervals to analyze. Cut at -3, cut at 0, cut at +3. Highlighted in yellow, just to remind us, those are critical values. that are going to demarcate intervals where it's concave up versus concave down. They're the boundary values now. So 4 regions to test. And the thing we're testing is f double prime. So let's put that above. I want to use a slight shorthand that I'll only use inside this interval here. Otherwise, it's too much to write in. When we say concave upward, I'm going to write that in as concave upward, CCU. And when we say concave downward, I'll write that in as concave downward, CCD. So next thing to do, actually test these intervals. But if you like that idea of a shortcut, let me show you what it would look like. I'll do the full method, all the tests of the regions, but let's see what the shortcut actually looks like. First thing I would test is probably the very far left one. Pick a value, say -4 would do the job. Then take your -4 value, plug it into f double prime. This is not a good spot to plug it into. We're going to plug it into way over here. F double prime -4 is going to be equal to, well, this is 4 times 16. This is 16 plus 9, so 25. Notice on the very first 3 terms, always positive. And there is nothing you can put in for x to make the first 3 factors, rather, not terms. These are always going to be positive for all x. Here's where things start to happen, though. That's going to be a -1 when we throw in a -4. This is going to be a +7. The power 2 here says the denominator is always positive. But just for the sake of showing it, let's throw in the value of -4. 4 plus 27 squared. Everything here is positive, except that one factor. One negative sign means the whole result negative altogether. So we can come back here and say, this one is negative. So on the entire interval from -infinity to -3, concave down. Here's where I would take the shortcut next. Concave down happened at -3. And -3 is relative to this one. It has power 1 right here in the group, which is odd. I expect then a change to positive. Now, if I change that to positive, though, will I change it again to negative? Look at the 0 here. That critical number came from x squared. That power is even now, and that means no change in direction. I claim it's going to be positive, but we'll check it out just for extra assurances on that. Now, after I get the positive on that, I look at the 3. You always go back here, take this 3, find where you got it. That's really important too. Came from here. Power is 1 on that group, which is odd. So I do expect another change. Less than 0 on this one. So if that really works out, and we're going to double check this for sure, I'm claiming concave up, concave up, concave down. So that check is a huge time saver in a problem like this one. But it's also a dangerous check. There's lots going on when I say, look in the intervals. If the outer power is even, no change in sign. The outer power is odd, you do change sign, but that is tricky. That's something to practice. So let's just double check everything. I'm going to take the -1 in this region and hopefully show we get a positive second derivative. F double prime -1 is, here's the second derivative. Up here, that's -1 squared, so just 4. That's 10 now altogether because of the power 2 on x. This will give us a 2. This will give us a 4. And for plugging in -1, any number you plug in down here, it's always positive. This one is going to give us 28 squared. Whole thing is positive as we expected. But this is really weird, right? You'll often might have noticed that these intervals usually change signs. This time it didn't. It's because of the power 2. If I plug a 1 in there, I still get a 4 altogether. So go f double prime at 1. When we put in a -1, the power 2 forced it to positive. When we plug in 1, still positive. It's still just a 4. Plug 1 here, it's now just times 10. Then this will be 4. 3 minus 1 is a 2. Whole thing is divided by still a 28 squared. And that means positive again. So the whole culprit of doubling up positive and positive, right there, power 2. Then let's do this last check just for the sake of total completeness. F double prime at 4. I claim negative. If we put a 4 here, that's 4 times 4 times 4, so that's a 64. 4 here is 16 plus 9, so 25. Feels like deja vu at this point. This will be a 7. And now we get a switch. This turns into 3 minus 4, a -1. But if it was a power 2 there, it would have been converted to a positive 1. This would still be greater than 0. It's because the power is odd right here. We get a -1 now. Divide by, oh geez, we put in 4 power 4 plus 27 squared. But it's negative just like the very first one was. One factor did the job on this. So we have negative as expected. And that tells us our sign chart is finally complete. All we need to do is just read this out. We can say F is concave. Let me write in this way. Concave up on -3 to 0, union 0 to 3. And notice the really weird way I wrote that in. There's no concavity right at 0 because the second derivative itself is 0. Concave up means positive, concave down means negative. So if I'm reporting concave up, I actually had to break up the interval to delete the 0 value. It's not from -3 to +3. That's enough to miss the question WebAssign. You wouldn't miss much points on a real exam question. That's a slight subtle thing, but something to watch out for because it could be a frustration. Next, we say F is concave down. On, well, this one is coming in 2 regions as well. It's from -infinity to -3, union +3 to infinity. So that takes care of concavity finally. And again, if you have a feeling of deja vu from the increasing decreasing test, that's good because algebraically and with the calculus, it's exactly the same steps other than we based it on the second derivative for critical values, which means it's not about increasing or decreasing. It's about concave up, concave down. Well, our next one is inflection point, but I don't want to rush through that one. I think it'll make more sense to come back on Tuesday, refresh our concepts on concavity. Then we'll look into the inflection points and when the world is going on with this new method where conclusions seem to be backwards. We'll justify that and then move on to this optimization technique down below. So that's the plan so far. Once we conclude this section next Tuesday, we'll move directly into the next optimization section, 4.3. But any questions at all, folks, with what we've done so far?
Yeah, when finding the critical numbers, you didn't get a critical number for 9 plus x squared because it would equal x equals, or it would be square root of -9. Is that why?
Exactly. Upon taking that square root of -9, we have an undefined value.
Oh.
I mean, it really is defined, but it's a complex number. So for this course, we regard it as an undefined. That's also the reason simultaneously why we couldn't factor it as well. Other questions at the moment? Okay, well, have a great weekend, folks. When we come back, we'll be finishing off 4.2, moving into 4.3. And that means we're just about done with chapter 4 as well. 4.6 on antiderivatives will be the last one, so that we transition from differentiation, which we've been doing quite a lot of, into next integration, reversing the whole process of differentiation in a sense. But have a great weekend, folks. I'll see you all next Tuesday.
Hey Mike, I just had a quick question.
Yeah, sure.
So looking at the schedule, it looks like we're scheduled to have an exam the week of April 21st,
Yeah,
which is in 2 weeks. So how will it look as far as like what will be on exam three?
it's gonna be whatever we end on this week. Let me think about this. Hang on. Nope, it's gonna be whatever we finish on this week right here. So it looks like it's going to start on 3.5. Looks like it's gonna include 3.6, 3.7. Then it's gonna take 4.1, 4.2, probably 4.3, and 4.6. 4.6 might be the one that doesn't quite make it to the third exam.
Okay, perfect. Thank you.
Yep, absolutely. Have a great weekend.
You too. Bye.